Okay, next speaker is Renato Assunção. He's going to talk about how spatial clustering and regionalization of small areas with Bayesian methods.
I have to ask for, there has been two changes in the program. First, the person who should be presenting, Leonardo Teixeira, he could not come to the meeting, and so I'm presenting. I'm the second author. And in the title also, I forgot to change the title from one old presentation. And I decided also to just start in a little bit different way. I mean, I will just show what we have been done, but this started a long time ago, and with one method that I developed with a bunch of friends and colleagues to do regionalization of spatial areas. And for my surprise, and I was very pleased to know last week that ArcGIS-Pro implemented this method in their ArcGIS Pro software. ArcGIS, if you don't know, it basically dominates the software, the GIS market. Basically, they have 95% of the entire market. So what we have done here, it's a follow-up of this work. It's a Bayesian version of what we have done in the past. This is the manual page of ArcGIS. And you will see some plots like this one by the end of this talk. So this Bayesian work started with when I coupled with Rosângela, and we start to work with this, and then Leo came, and let's see here. Does anyone know how to visualize this PDF? And really bad, but anyway. This is one of the many visual tools for PDF in Linux. So, great. So, can I just go here? Yeah. Okay, so the motivation, thank you. The motivation is started with this Atlas Cancer of Mortality. This atlas is produced in many countries, and we have hundreds of them for each one of the different sites where you have cancer, lung cancer, bladder cancer, and for the different sex, male and female, and many times also for different races, white, black. You have a different map, like this one, which shows the lung mortality cancer for white male in the United States. You can see very clearly a spatial pattern in the map. But then you have another one. This is the heart disease for white male, and then you change for lung cancer among the white female. Is quite different from the first pattern, which was for male. So one purpose here is to try to, as all statistics does, try to summarize this complex pattern, spatial pattern, in a way that makes things more easy. A picture like this one would be much more simpler to understand and interpret and maybe take decisions. The idea is to aggregate areas in larger clusters, contiguous areas, in such a way that the areas has very similar areas, very similar values inside each one of the clusters. So in each one of the areas, we have a feature vector composed by k covariates or features, and the spatial clusters, which are represented here by the different colors, they should contain contiguous areas and similar areas with respect to x. So there are a few applications to do this, but let me go directly why a Bayesian approach would be interesting here. One of the reasons, among others, one of the reasons is that most regionalization techniques, they consider the data as fixed static values. And it means that the features in the vector x do not have any kind of uncertainty or error. This assumption is quite inappropriate if you are working with vital rates, like number of deaths divided by the number of the risk population in a certain area. And when you do this, if you go ahead with the regionalization techniques that are implemented in many softwares, which are typically purely algorithmic methods, what you get is something like what you see here on this side, is a highly irregular division of the area, just going around on each one of the small values, different values that you have. And this is many times caused by simply because the rates are highly, have very different variances. And some of them are extremely high. For example, for infant mortality rates, which is not a common event, typically less than 5% of the children die in their first year, even in very poor areas. So in a small population, the rates will have very large variances. In one single death, additional death can produce an extreme death rate. So if you see here the number of children in the horizontal x and on the vertical, the infant mortality rate, and on the right-hand side, the log for the same, the horizontal x in the log scale, you see very clear a kind of funnel type aspect of the plot, because here we have very extreme variances. That's why you see values very high like this one, or values that certainly are subestimating the risk when you estimate the infant mortality rate is equal to 0. Of course, it cannot be 0. It's higher than 0. You know already even the side in which you are biasing your estimate. And here, when the number of children is high, is everything goes okay. So what this implies, and you can see this not only for infant mortality rate, everything, lung cancer, bladder cancer, whatever kind of cancer or vital rate that you look at. What is the consequence? Is that if you are trying to aggregate areas, ignoring this uncertainty, what typically happens is that if you have one area with a large variance surrounded by others, if it has a very large variance, it will look very differently from its neighbors. And typically, you would separate out this area, forming a new cluster. So, okay, our proposed solution, and I will go, I don't think that, how much time, because I lost here a lot of time in the beginning. How much do I have? 15? Okay. So probably I have to skip a few technical things, but basically the idea is that we propose a new method which combines two key aspects in this regionalization. A stochastic Bayesian model for the data, for the parameters, and for the partitions. That's because what we want is to partition this map. We will imagine that this is unknown, and we'll put a probability distribution on that, a prior distribution, and we'll get a posterior. And the second main key aspect is that we used a tool called the spanning tree, a graph definition, to explore this space of all possible partitions. You will see why we have used that, and this is really key. A preliminary version of this paper appeared in the IEEE proceedings of the ICDM. There are a lot of related work. I will not have time to go explaining all of them. These are basically algorithm procedures, not the stochastic ones, but of course, we are not new in the area. There are several other Bayesian approaches, including a very recent and very nice paper by Page and Quintana, Fernando, who is here, that was published in Bayesian Analysis last year. So I will not have time to describe in which way our work differs from all of this, but if I can summarize, the main difference is spanning trees. The use of spanning trees as a trick, as you'll see. So, to explain what we did, we can see the problem as a graph problem. We have here the map of Belo Horizonte, and the areas are connected if they share boundaries. So if they are neighbors in space, we connect them. We want to get something similar to what you have on the right-hand side. And to make that partition of the graph, you want that the areas that stay together, they are very similar with respect to some underlying measure, some underlying rate, some underlying something that you don't see, but the data give you some idea of what it is. So how to do that? Well, if you try all possible partitions, it's just an unfeasible problem because it's just too many ones. It's explosively, exponentially, it increases exponentially with the number of areas. So there is no way you can go on looking for all possible partitions. You have to find some other way to go around this problem. And what we use is what we call the spanning tree. Here we have the original graph on the left-hand side. On the right-hand side, we have one spanning tree. There are many spanning trees associated with this graph. What is a spanning tree? A spanning tree is a subgraph of the graph, of the original graph. It's a special subgraph. It's a subgraph where if you have any areas, you have n minus 1 edges connecting these areas. More than that, you always have one path connecting one area to any other areas. Let's say, for example, this area here, and let's say this area here. There is one single way to go from this area to that other one, and I think it's this one that I made here. Something is wrong here because it seems that there is two here, but it's just one. So that's the definition of one spanning tree. And you have many possible spanning trees on this associated with a single, one specific graph. So you can imagine a set of possible spanning trees, all possible spanning trees associated with this graph. What is in this spanning tree? Why it is interesting? Because one very nice property of spanning trees is that if you cut a spanning tree, if you just take out one single edge, you immediately split the areas in two connected subsets. So the problem of if you take out two edges, you immediately get 3 spatial clusters. If you take 4, and you have only n minus 1 to test if you have one fixed spanning tree. So it's a very fast way to create clusters if you have one good spanning tree. So if you have a good spanning tree, you only have n minus 1 rather than an exponentially large number of possibilities to test and select clusters. So the overall idea, that I will not have time to go on the details, is that we, if we have a given partition of the data, if we have a given partition of the map, we have the usual Bayesian model for the observed data in each one of those clusters. We assume that the data are independent inside each one of the clusters. So given the partition, everything is trivial. Now, then, given a spanning tree, a prior probability for the partitions that are compatible with that tree, that can be formed by deleting some of the edges of the spanning tree, is put. I mean, we put a prior probability on these partitions, which are simple, very few ones. If you want to divide in 2, you only have n minus 1 possibilities. If you want to divide in 3, you have n minus 1, n minus 1, 2, the binomial number. And I will use this notation. Pi is compatible with the tree if I can get the partition pi by deleting some edges from the tree. How about the spanning trees? Well, they are selected uniformly from the set of all spanning trees. That's our hierarchical model. A set of spanning trees associated with the given neighborhood map graph that we start with. Then the nice thing is with this spanning tree trick, we were able to obtain a full conditional for each one of the components, the partition, the tree, the spanning tree, plus the other parameters, the usual one. And so we could run a Gibbs sampler a simple Gibbs sampler procedure on top of all of this. How much time? Still have? I lost here.
10 minutes is the question.
Okay. So maybe some of the steps are just trivial, usual Bayesian things. The nice thing is about these partitions and the trees. So let me just concentrate on this part here. If we say that we have a spatial partition model. Now, at that time we created this, your paper had not appeared yet, Fernando. So I think we have maybe to change the spatial partition model here. Product partition model, SPPM. This is the simple part. Yeah, when it changes here, given the tree, a partition that is compatible with this tree, the probability is proportional to the product of cohesion measures. Cohesion is simply a number that you associated with each one of the graphs. It gives a lot of freedom here for the user to model in which way he wants. For example, it could depend on the topology of the spatial cluster that you create. You don't want, for example, you could not want spatial clusters that are too long or that have long arms, you want them compact or something like that. We have not done anything like this in our implementation and in our examples here. We use just this very simple one here. It's just a partition, a probability of a partition depends only on the number of clusters that are present, not where they are or how the shape they have, although you could put this. So we just use this depending on a parameter rho. And in a way, this parameter rho can be interpreted as the probability of removing an edge of the tree. So it gives a good idea of how many clusters you can get at the end. And we will be assuming a beta prior distribution for this rho in this specific implementation of our SPPM. We assume that the trees has a uniform distribution, the spanning trees. And for the sampling distribution, most of the steps are just usual vanilla kind of Gibbs sampler calculations. Maybe the interesting ones is this. For the tree, we assume that we get that the tree given the partition and the data, it's just a uniform distribution on the partition, on the trees that are compatible with that partition that you have. We have here then an algorithm to sample uniformly a spanning tree. And finally, sampling the partition is given the data, the tree and row. We have an expression. It depends on the predictive distribution for the y's. This is the y's inside each one of the spatial clusters. It's a product over the clusters plus this rho times 1 minus rho. So we can integrate out this rho parameter, obtaining pi given only the y and the tree. So this can speed up a little bit things. And this f of y, depending on the model that you have, it can be easily obtained. We have done some examples with Poisson and normal where this calculation can be done analytically. To sample the partition, because this is the joint distribution, I mean the distribution of the partition as a whole, so how exactly do we sample from this partition? The interesting thing is that because we are sampling a partition conditional on the spanning tree, it's very simple. The only thing you have to do is to select which one of the n-1 edges that you're going to delete from the spanning tree without worrying about consistency of what you get at the end. And when you do this, you can just go on each one of the edges. This yi is a binary distribution to decide if you are going to delete or not that edge given what you have decided on the others in the tree. So it's very simple. It's a Gibbs sampler in the very nice way. It again depends on the predictive distribution of the y's. And so the other parameters are just plain simple things. So let me go directly here to a simulation in the 5 minutes that I have, just showing some results. First, some simulated data. We reproduced more or less some of the numbers and values that we see in some real cancer maps. And we got the south region of Brazil. And we basically got two different situations, one where the risk is a little bit high, like lung cancer, and another where the risk is very low, like blood cancer. We have a lot of evaluation metrics trying to our estimate is just the usual average, and we just calculate many of them, the usual posterior average, and we just calculate several different metrics, including some that are more common in machine learning literature. And we have here not the Bayesian methods, although we have already calculated and tested our methodology against the Bayesian methods, and the results are very good. We beat them all. I'm not showing those results here. I'm just showing some of the other that are common in the geographical information system literature. And this table is not here for you to read the numbers. It's just to see this bloat, which is the best result in each one of the different metrics that we look at, and this is connected with our method, except in one single case here, which was better than ours. This is for the situation where you have a low rate and a common parameter. This is a different simulation where you again have a very low rate, but a distinct parameter for each one of the areas that are inside of cluster. So again, we have very good results. And just to show some pictures, some maps. These are lung cancer and blood cancer, south of Brazil. So because we have a Bayesian analysis, what we have is not one single partition, but in fact a distribution where you have many possible partitions, a posterior distribution. So this is an example of different partitions. I don't know if you can see the divisions here in these black lines. These are the divisions, the different partitions for the lung cancer example. These are the true numbers now, it's not simulated numbers. So this is the lung cancer. So how to summarize this? One way that we thought is this, two ways in fact, there's two maps here. This first one, what it does is, when two areas, they are most of the time together in the same cluster, we do not put the edges. We just have the colors of the original rate drawing the map. When two areas, neighboring areas, do not share the same cluster very often, in this case I think we use 90%, 85%. 85%. So if it was less than 85% of the times together, then we draw the edge. So what you see here are the areas that you cannot assign very clearly to one cluster or another. These are in a way the boundary areas, the areas that really are dividing the clusters. Of course there is a lot of uncertainty in here, so but then what you see here, for example, these areas are the ones that you cannot clearly assign to the right or to the left. And this other map here, the color is associated to the average of the group size to which the area belongs throughout the sampled partitions. So very dark areas means that the area belongs to a very large cluster. And very light areas means that the cluster in which it belongs to, most of the time, is a tiny, small area. So these are some examples here of what you get with the same data with other maps or other procedures. Basically one single partition, and many times not very good compared to what we got. In this case, since we don't have the real truth, it's difficult to say which one is really the best, right? So in conclusion, in this work we propose a new regionalization method. It is a Bayesian model allowing for any distribution of the data and for different variances. I presented only the situation where we have only one variable in each one of the areas. It was a Poisson number. It incorporates the spanning trees as a tool to explore the partitions of the data set. We compared its performance against the main competitors in simulated data sets, showing consistently better results, and we illustrate the method with 2 case studies. In fact, I just showed here one. So, thank you very much.
Well, maybe one just quick question, if anyone.
Sorry, is it working? Oh, okay. So, a very nice presentation. I have several questions, but I'm just concentrating on one. What happens when you want to incorporate one new extra? Let's say you want to predict for a new area that you haven't explored yet. What happens in that case?
To predict a new area?
Let's say you want to add a point that you don't really have right now to your collection of things. You want to do predictions. When you do predictions, does the same spanning tree work? Or you have to do kind of like the whole thing together again?
You mean you enlarge the map? Suddenly
Yes.
it's, oh, no, yes, you have to start all over again because it depends on the neighborhood structure and so on, yeah. Oh,
Okay.
It's, in this sense, if things are coming in a stream, yeah. So good point, I didn't think on this. Yeah.
I can talk to you later.
For point patterns, that it could be a problem.
Let's thank Renato again.